Perfect. All right, thanks everyone. I'm Mike Fitzgerald from UCLA, and it's my pleasure here to talk to you about HiSpec, where we are with the development. I'll be speaking on behalf of the HiSpec team. Here is the instrument team. Dimitri Mawe, myself are the co-PIs. Quinn Konokaki is our project scientist, and we have a host of people at the executive level responsible for the project. We have multiple subsystems, a lot of subsystem leads, a lot of activity, Caltech, UCLA, UC San Diego, and the observatory, as well as contributions from other partners. We have an additional science team, which I'm not going to go into because we're in the midst of full-scale development of this instrument. HiSpec is primarily designed to detect Keck planets at high spectral resolution. So it is designed to do so through a variety of means of direct and indirect characterization. And the advantage is the spectral resolution that we're going to bring. So we'll take advantage of high spectral resolution to distinguish features from exoplanet hemispheres from their host stars and get at a variety of science. The basic requirements for the instrument are listed here. We're operating over a broad range in the near infrared simultaneously. We go from wide to K bands at spectral resolution of greater than 100,000. Good sampling of the line spread function. And we're really trying to optimize for high efficiency. The exoplanet science that we're trying to enable is really set by the fact that we're using the spatial filtering properties of single mode fibers. But in order to do that efficiently, we need to really optimize throughput and coupling efficiency into those fibers. That's made possible by the Keck 2 AO system, but also aspects of our design and the development of transmissive infrared fibers like Z-band materials. So we have multiple modes. Relative high sensitivity, which I'll show, enabled by that end-to-end throughput. And we're aiming to be able to do precision radial velocities. Another key feature of our design to try and characterize exoplanets through a variety of means. And so we're aiming for an internal velocity precision of better than 30 centimeters per second. There are three primary observing modes and how we're going to be using the single mode fibers to feed these spectrometers, the spectrometer system. There's direct spectroscopy where you just center your object onto the single mode fiber, you couple direct light into that fiber, and it gets output in the back-end shell spectrometers. We can do off-axis indirect spectroscopy where for example, you're looking at a resolved star-planet system where the star is off-axis from the planet, and we're injecting the planet light into the same fiber. For very close-in systems, where the separation is less than sort of lambda over d, we can take advantage of interferometric techniques. This is a vortex chronograph, where we place that in the pupil plane, and that rejects the on-axis starlight. It is perfectly canceled by the symmetry of the system and the spatial filtering property of the single mode fiber, whereas off-axis, slightly off-axis planet light does couple in with some throughput. So this is a high contrast mode enabled by the instrument. Here are some recent simulations showing the sensitivity, point source sensitivity. So 4-hour integration. This is signal to noise per resolution element, showing that we're reaching this 15 Vega mag limit at relatively high SNR. So a very capable instrument. We're also aiming to really do our homework here on the internal radial velocity precision. So Ashley Baker has led a detailed error budget. We're focusing at the system level for how to achieve high precision for radial velocities. Now, all of this together is done in an instrument. We're in the midst of the full-scale development. There are multiple pieces to this instrument. The front end, where we inject light into the fibers, is on the K2 AO system. There is front-end instrument on the K2 AO bench that we're designing. That light gets coupled into a fiber subsystem, which transports the light down to the basement of the observatory, where we have the back-end spectrometers, associated electronics racks, fiber switches, as well as calibration racks. So a lot of the action is down in the basement where things are a little more stable environment. The front end instrument, as I mentioned, goes on the K2 AO system. Here it's shown on a service cart ready to be installed. There are multiple pieces of this instrument to try and get light efficiently coupled into those fibers. We have a tracking camera, which watches the position of the star relative to the fiber and steers a field steering mirror. Light is split by dichroic into our YJ and HK channels, so simultaneously feeding two different fibers. We have some beam shaping optics to maximize the efficiency of the light injected into the system before it's transported down to the basement. The fiber delivery system is complicated. So in order to enable all of these different modes, multiple calibration sources, and an ability to cross-calibrate the system, we have multiple switches where we can route light between different fibers and go all the way back up to the front end instrument and the Keck 2 AO enclosure, as well as back down to the basement dewars. And so two different vacuum cryostats that are fed by the fibers. So complicated fiber switch system, but still designed with an eye towards efficiency. This is also enabled by mechanical fiber switchers, as well as MIMS switching that switches light between the fibers. And those are under prototype. I'll show a little bit. The back-end spectrometers we're designing at UCLA in the midst of mechanical design, detailed design here, where we've got each cryostat has a pair of 3-mirror anastigmats, a collimator and a camera. Those feed an Eschel grating and a cross disperser made out of single crystal germanium, the very beautiful gratings we'll show. And so we've got those inside a vacuum enclosure designed by the observatory. We're in the midst of designing this. We're aiming for a manufacturing readiness review later this year. These are the two contributions that I want to highlight from our partners from the Astrobiology Center. This is one of the single crystal germanium gratings. This is an exquisite grating. This shows a scanning electron microscope image of the grooves. They are just nearly flawless. So we're reaching the theoretical diffraction limit, very close, very low wavefront error. We've optimized the apex angle with rigorous coupled wave analysis to get the best efficiency from these gratings. We've also been prototyping robotic fiber switchers to decouple and recouple the single mode fibers and enable the switching. UCSD is leading the calibration subsystem. They passed their manufacturing readiness review. There'll be multiple modes of calibration, including the laser frequency combs at Keck, as well as Fabric Pro Etalons, gas cells, our polycathode lamps, flat fields, et cetera, and the solar. Where we are with the project in the midst of our full-scale development, the key highlight date I think people want to know is when things get to the observatory. The current schedule has that in the second half of 2026. So to summarize, we are in the midst of developing high spec enabled by single mode fibers, precision spectroscopy for exoplanet characterization, multiple modes of operation. We are in the midst of full-scale development. We have the funding for the instrument. Most recently secured a gift from a grant from the Gordon Betty Moore Foundation last week. So that brings us to complete project funding. We're doing manufacturing readiness reviews for our subsystems, and we're in the midst of full-scale development with integration starting at the end of this year and continuing on through 2025. All right, and that's it. Take care.